So now in this video, we're going to look at a non-inverting comparator circuit, but we're actually going to use a comparator integrated circuit. Normally I use an op-amp. So this is an LM393, and it behaves, when it comes to the inputs, it behaves the same, but the output behaves differently than the op-amps I've been using. So in any case, we have a high input right now, and we have a high output. Red LED is off though because I have it wired to light up when the output is low. Transistor turns on when the output is low. We will look at that later. I lower the voltage below halfway because that's what we got set there. And it's not Schmitt trigger, so there is a middle ground region right there. But in any case, low, negative supply. Input, we have a low output, and the LED is on. So now the LM393 does not produce a positive voltage when the output is high. It's basically off. And so we have a pull-up resistor, so we can get 5 volts at this point right there. The output can go low, connects directly to ground, and so we will have current that goes through there. We'll just go directly to ground. Now, when it comes to the load right there, we have a PNP bipolar junction transistor. I'm using the 2N3906 right there. And when the output is low, connected to ground, you can see that little current path right there. Because again, we got a 10K resistor going to ground. That allows many times the current, maybe 200, 300 times as much current to go from positive to negative. Of course, that's how much the transistor will let flow through. The load will limit the current based on 5 volts across the load right there. Basically, the transistor will be conducting perfectly well, but the load will set the current. And again, it's a comparator integrated circuit. It's looking at the two voltages, and the output's either going high or low, although we did see a middle ground region where it looked like it wasn't connecting to ground perfectly, so it may have been limiting current. But as long as we get high enough or low enough here, the output's gonna actually come from the positive supply, locking the transistor off. You can see positive on each side, no voltage difference, no current flow that way. Basic PNP bipolar junction transistor rules. If we set the trim pot low enough right there, below, enough below 2.5 volts, not much more below 2.5, but we saw right at probably about 2.5. We kind of had a middle ground region. So in any case, we do have to get low enough, but not terribly low right there. Then the output will be low. It'll connect to ground perfectly well, as I said before, and the transistor will turn on. So when it comes to the output, so again, we're using just the one on the left. We have our trim pot going to the plus there, our fixed resistors going to the negative, and the output. So the pull-up resistors to the positive supply there. We'll take a closer look at it. And then the other resistors going to the transistor. This is inside the integrated circuit. There is a bipolar junction transistor because it's open collector right there. And bipolar junction transistors have collectors. It's an NPN version. But in case, it's built into the output. And it's either off, so it's basically like this. You got the pull-up resistor that can give a +5 voltage because it's off, or it is on. It's connected to ground. And so you can have, current go through a load. I mentioned this in the pull up and pull down resistor videos, that when you got a pull up resistor, the pull down part, the switch inside, this is a transistor switch, can power a load. And so we could do that with this, even though we do have resistance there in a transistor. But in any case, that's the transistor on. It can power load, but when we turn it off, we have that pull-up resistor that provides 5 volts, but is not meant to power anything. So, like with this transistor, it's going to enjoy having direct connection to ground while it's on completely, and then having this pull-up resistor, making sure it turns off completely, because maybe we will kind of get some stray voltages there, and because it's just floating in the air. We've looked at that in other videos. So apparently, I made this diagram a long time ago. Apparently the data sheet I looked at said to limit current to 16 milliamps when you're syncing. So be aware of that. Another good reason to use the transistor right here. Always consult the data sheet. Now, we will actually look at the circuit because we kind of covered everything. So this is a 2N3906 PNP. Because all we're doing is lighting the LED, we're going to look at another video with a higher power load that the 2N3906 will not be good for. But in any case, it's perfectly fine for the LED right there. Positive supply, the emitter, base, we got our resistor there. Right now the output's low, so the transistor's on. And we got the load lit up. There's our pull up resistor right there. Our two equal value resistors, 10K, going to the inverting input. You could use different values as long as they're equal, no problem. And then we have our signal right there, the trim pot. And of course you have to power the integrated circuit, positive supply pin 8 and a negative supply to pin 4. If I raise this above halfway, there is a kind of a middle ground region right there, but very, very small right there. But yeah, we get it high enough, then the transistor's off because we have a high output, which it's off actually. It's not doing anything internal. We just have the positive there, locking the transistor off. And even though I have this side floating right there, the power supply says it doesn't have to provide any current right there. So we probably aren't providing any current. It's probably locked off pretty solid right there. But in any case, that's about it. Hope you enjoyed. Make sure you check out one of the other videos I'm posting on the screen and check out the links down below. They all help out a lot. I'll see you in the next video.